Hello everyone. I am Gofi Hong from USTC and Shenzhen Institute for Advanced Study. On behalf of all the authors, I am very happy to present our work. Learning robust policy for multi-UV collision avoidance via compact causal feature. Let me first give you a quick outline. I will start from the background and motivation, then describe our key insight on compact causal features, then introduce our CCFL framework with 2 modules, present experimental results, and finally conclude. Multi-UV collision avoidance is critical in many real-world applications, such as infrastructure inspection, delivery, precision agriculture, and emergency rescue. In these applications, collision avoidance is essential for UV. Recently, deep reinforcement learning has become a popular paradigm because it learns end-to-end policies directly from depth images, outperforming handcrafted pipelines. However, DRL implicitly assumes the train and test distributions are the same, which rarely holds in the real world. Due to limited generalization, UVs may fail in unseen environments, leading to economic damage and threat to personal safety. So the core question we ask is, how can a swarm trained in one environment fly safely in unseen environments, with different visuals, obstacles, and dynamics? To answer this, we ran an experiment. We take SC-Ray, a representative DRL baseline, and train it in a playground. When we deployed it directly in a forest, the swarm success rate fell to 0. We then asked, which component is failing, the visual encoder or the policy network? We fine-tuned each one separately on the forest environment. Fine-tuning only the visual encoder lifted ISR from 51.9% to 88.6%. Fine-tuning only the policy network barely changed anything, still around 48%. So, the visual representation, not the policy, is the bottleneck of generalization. The reason is that the encoder encodes all information, including non-causal and redundant components, which limits generalization. The takeaway is clear. Learning compact causal features is crucial for improving the generalization of deep reinforcement learning. This naturally leads to our key insight. We organize visual features into 3 layers, shown in this figure. Using a UV obstacle avoidance task as an example, the outer ring contains non-causal features such as background texture and obstacle shape. They are environment-specific and do not transfer. Inside the causal ring there are still redundant features. For example, UV texture or details of crashed UVs, which are causal but irrelevant to the avoidance decision. What we really want are the compact causal features, such as obstacle distance and UV velocity. They are domain invariant and task relevant. So our goal is to extract these compact causal features in 2 steps. First, identify causal versus non-causal, then compress redundant information. This is the architecture of our CCFL framework. It has 2 stages. Stage 1 is representation learning. A V encoder produces visual features, and our causal feature identification module disentangles them into causal and non-causal components, using contrastive learning under causal interventions. Stage 2 is policy learning with SC. Inside the actor network we insert the redundancy feature compression module, which uses a differentiable binary mask to compress redundant channels. Therefore, the representation fed into the policy is both causal and compact. Let me zoom in on the CFI module. Its goal is to disentangle causal and non-causal features by hard contrastive learning. First, we construct positive and negative sample pairs. Positive pairs consist of an image of a sphere obstacle in the playground and an image of a cube obstacle in the forest. They are put together, because they represent the same essential avoidance behavior despite differences in obstacle shape or background. Negative pairs consist of an image of empty playground and an image of sphere obstacle in playground. They are pushed apart because they represent different collision avoidance behaviors due to the presence or absence of an obstacle. The objective combines HCO loss and VE reconstruction loss to ensure both invariance and fidelity. After causal and non-causal features are disentangled, only the disentangled causal features are retained for policy learning. Now the RFC module. Even after CFI, causal features may still contain task-irrelevant redundancy. RFC removes this with a differentiable binary mask. Given a trainable weight vector W, we pass it through a small MLP plus real U. To get W hat, the mask is computed as W hat squared over W hat squared plus epsilon, producing values close to 0 or 1 in a fully differentiable way. The refined feature is just the input multiplied element-wise by this mask. The mask is supervised jointly. The actor loss J, pi, drives it to keep task-relevant channels, while an L1 regularization on the mask promotes sparsity. If the mask incorrectly suppresses a useful channel, the actor loss J, pi, increases, prompting the mask to self-correct. To validate the effectiveness of CCFL, we built a high-fidelity benchmark based on Unreal Engine and AirSim. During training, multi-UV collision avoidance is learned in a playground scene containing only one cubic obstacle and one spherical obstacle. During testing, the learned policy is evaluated in a forest scene with 22 unseen obstacles, forming a typical out-of-distribution (OD) setting. These are our main results on the unseen forest with 22 unseen obstacles. These are our main results on the unseen forest with 22 unseen obstacles. The baseline SAC加RA achieves 0 swarm success rate. Some UVs get through, but the swarm never arrive together safely. We compared with 5 strong methods covering augmentation, regularization, attention, causal disentanglement, and causal feature selection. Each provides only marginal improvement on swarm success. Our CCFL improves swarm success rate from 0 to 61.6%. Individual success rate by 42 points to 93.9%. And SPL by almost 36 points to 79.9%. At the same time, average speed and extra distance remain competitive, showing that we improve both safety and efficiency. To verify the result is not specific to a forest, we built 2 more unseen scenes: a snow mountain and a canyon, with the same obstacle settings. In every scene, the baseline collapses to 0 swarm success. CCFL recovers significant swarm success and pushes individual success rate above 90%. In all 3 scenes, this confirms CCFL is robust across visually distinct domains, not just one. Quick ablation: each module alone is not enough. CFI alone gives causal but redundant features. ISR is decent but SSR stays at 15.2%. RFC alone compresses. Without the right causal cues, performance drops sharply. Only when CFI and RFC are combined do we obtain compact causal features that synergistically push SSR to 61.6% and ISR to 93.9%. To conclude, first, we find that DRL generalizes poorly in multi-UV collision avoidance mainly because visual representations contain non-causal and redundant information. Second, we proposed CCFL, a unified framework combining causal feature identification with redundancy feature compression to learn compact causal features. Third, experiments show that CCFL consistently outperforms state-of-the-art methods, significantly improving robustness and generalization in unseen scenarios. Compact causal features unlock generalizable, robust, and safe multi-UV navigation. Thank you very much. I'm happy to take questions.